Hey everyone, welcome to another deep dive with me and Erik. This week we're looking at the zebra puzzle exercise. I think this is one of the most interesting videos we've done, and we're going to do it slightly differently to the normal videos. Normally we sort of start at some basic solutions and then look at some more complex approaches. Today we're going to do something slightly different. The solutions to this exercise, the longest one is 500 lines of code, so we're not going to be able to talk through line by line what's going on. We want to give you a few ideas of the different ways you can solve this exercise. And we're going to start with two ways that I think are the most interesting, and then look at some of maybe the more common ways or some of the more natural approaches is maybe a good way of saying it. So it's going to be a really interesting video. If you're not familiar with Zebra Puzzle, the idea is that you have a series of rules. I'll put them on screen here. You can see various statements. So we've got a village with 5 houses. The Englishman lives in the red house. The Spaniard owns a dog. And then from these combination of rules, you have to be able to work out who lives, which of the residents drinks water, and who owns a zebra. Thus being called the zebra puzzle. So just to show you one solution to start with, this is a solution in Kotlin, and this is just a cheating solution. Who drinks the water? It's the Norwegian. Who owns the zebra? It's the Japanese. So this is the answer you're getting, but obviously we're hoping somebody's going to come with a slightly more interesting solution than this. So we're going to start off with one of Erik and mine's favorite languages, which is Prolog. And actually both of these first two solutions are Erik's. But if you're not familiar with Prolog, this is the sort of problem that Prolog was made to solve. It is we're solving this in 28 lines of code here, whereas when we look at Java, that's 500 lines of code. So this is sort of the bread and butter of Prolog. And if there's ever an exercise where you should try Prolog, this is the one. So Erik, good to see you. Thanks for putting together these fun solutions for us. Start us off with this one. Talk us through what we're seeing here.
Yeah, so Prolog is great at solving problems that are based on constraints. So we know a lot of things about our problem domain. So we know there are 5 houses and all the rules that you've just mentioned. So there's a very direct translation in Prolog. So if we start at the top, we see a predicate zebra owner with owners like a placeholder values, like you could interpret that as the return value. So we're going to fill that in and we're going to let Prolog actually fill it in with the right value. And then the implementation, which is the next 2 lines. So first we're solving the puzzle with a particular arrangement of houses. So that's how you read line 2. So solving, and we get back the arrangement of houses. That is the solution. So that's how you should read that. And then on line 3, we're doing sort of like pattern matching. We're saying there is a member in houses that follows the pattern that we just specified. So the first element is the owner. So that means that the elements within the houses, the first element is the nationality, and the second element is the zebra. So, and we don't care about the others. That's why we're using underscores. But we're saying, find me the element where in the houses list where the second element is a zebra, and then give me that the first element as the owner value. So that's basically the way that it works for water drinker 2, only then we use a slightly different pattern, of course. So the nationality, we call it drinker now. And the fourth element within the list, within that element in the list is water. So that's all maybe similar-ish to what you've known. But now comes the beauty of Prolog and trying to encode this in Prolog rules. So online is the meat of, is a predicate solve. So houses is there's a variable called house. We don't initially know anything about it, but what we're going to do is we're going to give Prolog as much information about houses that it can infer its actual contents. So we start out with saying, hey, there are 5 houses. So the length of houses is 5. Okay, the Prolog will remember that and just already reduce the possible values. Well, Prolog also knows, because it's length, that it is a list. So initially we don't know anything about it, but now we know that it's a list of length 5. So we know 2 things actually. And on the right hand, you see %1. Percentage is a comment, and 1 is the rule as defined in the README of the zebra puzzle. So the second rule, which you've already mentioned, is that the Englishman lives in a red house. And so we're using that member predicate again. So we're saying that somewhere within that houses list of 5 elements, there is a value that matches the pattern on the left. So the first value of that element is English, and the last value is red. So we've chosen a pattern where the nationality is at the first element, and the color is at the last one, the pet is at the second one, etc. So you could choose, basically you can choose whatever you like there, but we just chose this one. As long as you're consistent, it doesn't really matter. So that's the second rule. And then most of it are variations of these rules. They're just statements about a house. So that the coffee drinker lives in the greenhouse, etc. But there are 2 different rules that sort of have to deal with multiple houses at once. So you can have rules about this pattern holds for the house next to this house. So yeah, the one that you're now highlighting is saying that the greenhouse is next to the White House. So we're using the next predicate, which we have defined. And this will be probably a weird way to define this for many people. So append is a predicate that takes a first element, a second element, and that third element is the combination of the appending the first and the second element. So the way that you should read this without having to know a lot about it is that within list, there must be a sublist where the first element is A and the second element is B. So it can be anywhere within the list. It doesn't have to be at the beginning. It can be anywhere. Or on the next line, there must be a sublist where the first element is B and the second element is A. So that's what next to each other means. It's just, this is a different way of actually defining this, but this is enough for Prolog to figure out that rule and to apply it as a constraint and to reduce the problem space. And then there's a third way of doing things, which is that a house at a certain position has to match a specific pattern. So the middle house is where milk is being drunk. So that's what we're saying here. So houses can be unified. So the pattern that we specify on the right must match the pattern on the left. So houses must match the list pattern where we don't care about the first element, we don't care about the second element, but the third element has to match that specific pattern where milk is the fourth value. And then we do the same thing on line 19, but then for the first house, so we're saying the first element in the list must have the Norwegian as the nationality. And that's it. We just write them out. And then this is enough for Prolog to just figure everything out without us having to do any looping or querying, whatever. I'm just going to say Prolog, find it, and that's it.
Magic.
And it's magic, I think.
Yeah. There's not much more to say about this. I mean, this is literally the bread and butter of Prolog. You state lots of rules, you then ask questions, and it gives you answers. It's a beautiful way of programming. It's something doesn't necessarily work efficiently for everything, and it can be a complex way of writing things sometimes. But when you're trying to solve problems like this, there really is just no better tool for this at all.
True.
So yeah, definitely go and try Prolog out. Definitely try it for this exercise. I think it's just a brilliant exercise to play with it in. So we're going to go from there as our starting point to somewhere quite different now. We're trying to avoid this sort of looping, go through all the possibilities route that most people take. And so Erik's gone for a totally different approach in this second one, which is to write a genetic algorithm that calculates, where we've got a population of all of the possible different solutions, and we're going to try and whittle that down and have different solutions having children with each other until we find a solution that rises up and is the perfect solution. Is that a fair comment on how it's working, Erik?
Yeah. So I actually didn't want to write this myself because I thought that there would be somebody else, but I couldn't find it, so I had to write it myself. But we're basically, if you're a fan of Darwin, this is natural selection, but then applied to a computer. So we have to this is a little bit bigger than the Prolog solution, admittedly. So there are more moving parts. So bear with us. But
there are more files here as well.
Yeah.
Just
I couldn't have
clear.
put them
You
all
might
in
not
a
have
single
noticed that. You
file,
might have thought, yeah, it's a magic 18-line solution. It's not. There are multiple lines, but I think it's still smaller than just the looping ones we're going to see in a bit. Actually, Erik, it's not actually that verbose. But yeah, let's talk us through this one.
Okay, so on line 4 to 8, we have just our basic setup. So we have enumerations where for all of the different properties of the houses. So now, well, then it looks like we just on drinks water. It says solution.value.houses.first, which means that, well, there is something like a solution, and then find the first house where water is being drunk, and then dot nationality. So I guess that quite makes sense. So find the first house where water is drunk, and then give us the nationality. And then for the zebra one, it's, well, of course, the pet has to be zebra. So that reads quite well. It's using a bit of link. Of course, everything is hidden here. So solution is a lazy one. It's a lazy one because we only have to calculate it once, and then we can reuse it across drinks water and owns zebra. We don't have to calculate it twice, but that's just a performance tweak. But the solution is actually calculated by doing simulation.run. So simulation is like doing having our own little world, our own little population of, in this case, 100,000 people. And we're going to do, we're going to simulate natural selection. So we're going to start out with random people, random individuals, as they're called in the genetic algorithm. And I mentioned there are 100,000. And then we're going to do something akin to how natural selection actually works. So we're going to create the population. We're going to see if, so in a minute, we're going to see how we're going to randomly generate it. So, and then we're going to do the simulation for at most 1,000 generations. So generations are, well, the way that you are used to with generations is like you have parents and then you have offspring, and the offspring are a new generation. And then that offspring has offspring and you get a new generation, etc., etc. So that's what we're going to program here. So with our random population, we check on line 18 if the most fit person, so fitness in terms of natural selection is the person that is best adapted to their environment. And in our case, that's the house combination. So that actually matches the rules the best. And fitness is a score between 0 up until 1. And if it's a 1, it basically means this is the right solution. And then we just stop because there's no need for us to continue checking further generations. So then we hope to get there. Then we found the solution. But in most of the cases, we probably won't. So what we then do, we're basically saying, hey, this population, none of the individuals in it were right. But maybe if we try to evolve them, we can we can sort of improve upon it. And there are ways in which we can do that. So we do reproduction.evolve. So we pass in our current population and we get back a new population, which we override it here. So this is still sort of okay-ish.
I think it'd be good to start with this most fit calculation, Erik, just so we can see what that means. So I guess this is under selection here.
Yeah.
So this is the fitness function that determines the most fit.
Most fit is a property that is being calculated for house array. So you have 5 houses, of course. So that's what's being passed into fitness. So these are the 5 houses. And then what we do is we check all the rules. So we're using C# pattern matching here. And then whenever there is a house that matches the rule, we increment the score. And we do that for all the rules. And this time we don't need to go into how that matching is done. It still reads fairly well. So we have any house where the nationality is English and the color is red. And in the end, at most, you can have the score of 14. So there are 14 rules because the first rule was the length is 5, and we sort of have implicitly encoded that. So we divide the score by 14, and then we get back a number between 0 and 1. So 1 is our ultimate goal, but basically we're doing for every single individual in our population, and an individual is a combination of houses. We're going to assign them a fitness score, and we're going to use that.
Nice. So just to recap for everybody, we've got 100,000 people. Each of those people is a different, as you said, combination of these houses, and the five houses, different set of five. And some of them might be duplicates, some of them might be different. But we're going to, for each of them, work out how closely they align with the rules that we set at the beginning. And that's telling us effectively, is this person moving us in the right direction towards a solution?
Exactly.
If someone matches none of the rules, they're probably someone we don't really want to be considering too much. But if someone matches all of the rules or 90% of the rules, then we really want to throw a bit more focus at that person, which, as you say, is sort of natural selection in the wild, how that works. A zebra that can go and chase food and is very capable is likely to have more offspring than a zebra that doesn't. Okay, so that gives us that. Should we have a look at how then reproduction works, I think?
Should we maybe start with initialization, where we create the houses so that people know what that looks like?
Yeah, although I think that's quite obvious. But we can do. Yeah, maybe it's useful to understand.
Just so that they know that an individual has 5 houses, maybe, just to make it clear. So at the top, we have 5 read-only values arrays of all the, the nationalities and the colors, etc. So these are all the elements. And then to create the population, we create a size number of individuals, which in this case was 100,000. And for each individual, we're shuffling those arrays. So nations get shuffled, colors, drinks, smokes, and pets. So there will just be a random ordering of those. And then we're going to use those random orderings to create the houses. So the first house will have the first element in nations, colors, drinks, smokes, and pets arrays. Second will have the second element, etc., etc. So each color will be in exactly one house. That is important. So we are generating valid individuals. So once we start getting 2 houses with Norwegians, basically we could have sort of had that, but that will be much harder for the genetic algorithm to find an actual solution. So you could even consider this a little bit cheating, but this was just to get this working better.
If we didn't have that rule, then we wouldn't ever come up with just one individual, because the actual constraints wouldn't be holding anymore, would they?
No, we have to,
because...
Well, you could add constraints where if you would find multiple values of a single one, you would detract from the score. But you could also argue that if you would have an individual that has incorrect data, that it would not be alive, that would not be feasible as being born or whatever. So, nature works like that too. So, but
so we've got 100,000 random individuals. Some of them will be duplicates, but they're all sort of valid houses. Okay, cool.
Okay, that's all.
So we start off initially by looking through those and seeing if any of those are perfect. There is a chance that, of course, we just randomly generate one that does work. But presuming they don't, we then come over into reproduction, and we call this evolve.
That's
function.
That's the meat of the algorithm. So what we're going to do is, for each of the elements in our population, we're going to have to create a child. So we're doing a one-by-one replacement, I would argue. So so we had 100,000 individuals. So we want to have 100,000 children. And for children, you need to have, parents. And usually there are 2 parents, and at least in this model, there are. So what we want to do is we want to sort of have the parents that are more fit. So the parents that are like better solutions, that are closer to what we want to find, give them a slightly better chance of breeding or reproducing. So that is what we're doing with selection.tournament. And you want to discuss it now or in a sec?
Yeah, let's look at that straight away.
Okay, so selection.tournament basically saying from the entire population, we are going to get 5 random individuals, because that's how we specify the tournament size. You could there's a lot of parameters that you can tweak with the genetic algorithm. So I didn't do any tweaking at all. So this might be completely unoptimal, but it was enough to get it working. So we're basically saying, give me 5 random individuals. And then the tournament part is, we're going to select the one that has the highest fitness. So this is the bias towards having fitter individuals reproduce. So it could still be due to randoms that we're going to select the 5 worst people, but of the 5 worst people, we're going to select the fittest one. So but the key part, it's still random. So a lot of this is all random. We're not going to just select the best ones, although you could do that. There are genetic algorithm variants where you're always keeping the 10% of the best individuals, or 1 or whatever. But we're just doing complete randomness here, but with a slight bias towards the fittest individuals.
I think it's worth saying as well here that obviously in nature, there's an unlimited amount of parameters that might make someone more fit or less fit. Here, everyone has got a score of between effectively 0 and 14. I mean, I know it's reduced down, but there's only 14 possible scores that somebody can get. So the tournament is only, it's not it's a very discrete, is that the right word? Discrete set of possible values that you can have. It's not just like a big range of different possible scores.
So
okay, so this took me a little time just to understand exactly what you're doing when I first looked at it. But getting 5 random individuals, any 5, and then just taking the best of those 5. And then going back over into reproduction, we're calling that here, and we're getting 2 parents out. Therefore, could actually be the same person twice as well.
Could be.
Could be. But it's statistically not that likely, but maybe it's because we're reducing it down by 5, actually probably will happen in every generation. But again, that doesn't really matter. It just means that we'll be transferring 1-to-1 someone down.
I couldn't be bothered with doing a loop where it wasn't the same person. So this isn't a complete actual simulation of real life. So
we're not trying to recreate the world here. We are still trying to just solve zebra puzzle. And this is calling this reproduce method with the 2 parents, that there's a crossover and then a mutation, Erik. So talk us through crossover first.
So crossover is what you know from probably genetics, where if you have 2 parents, half of your genes come from your one parent and then from the other. So this is what crossover is doing. We're doing slightly, so you have different ways of doing that in normal genetic algorithms. What we do here is we're basically assigning, saying one parent is responsible for the nationality of the houses, and another is for the color, and another is for the drink. So we're sort of swapping between the 2. You could do this in different ways, but the key thing is here that you have to have one of the parents be responsible for all of its parents' children's value of a single property. So parent 1 is responsible for all of the nationalities, because if you would combine that, it could get into incorrect states, because you could have the same nationality twice, etc. And just this is a guard to prevent wrong solutions, basically. And then within that enumerable.range thingy, we're going to create the new houses. And then we're going to, based on that, what we did with parent houses, we're going to select the nationality, color, drinks. So the nationality will be from the first parent, the color will be from the second one, etc., etc. But we're doing that randomly. So it can differ. So in one time, but it's for a single individual, they will always get the same parent for nationality. But for the next crossover we're doing, it could be a different parent. So there is randomness there too. So again, randomness. Randomness is really, really important in genetic algorithms. And then in the end, we're just returning the individual with the houses we created based on the parents' values, and we're immediately going to assign it a fitness.
And so the key thing about this is if you ended up with the same pair of parents, it's a hard phrase to say, the same pair of parents, and did a crossover, you would still get a different child because of this, which is the key thing. There's not a linear relationship between the same 2 parents and their offspring. You've got that randomness that's built into that each time. And then once we've got that, Erik, we then mutate the genes of the child.
But you do that only. You don't mutate for everybody. So that's important.
No.
So you have a should mutate. So mutation rate is also a tweak point. I'm not even sure what I set it to. Maybe I don't even know. but
19.
19. So basically, about 1 every 5 individuals is mutated.
Mhm.
So no, 1 in 5 because it's less than or equal to. So
Mhm.
and then if there is a mutation, there should be mutation. What we're doing is we're gonna with a group random shared shuffle house indices. So we're gonna randomly select 2 of the houses. So we know that
Mhm.
these will be different because this is a shuffling. And then we're going to
Mhm.
select the one house and the second house and randomly do one of the actions that are defined below that. And that's basically
Mhm.
just a bit of C# magic to swap the nationalities, the colors, the drinks, the smokes, or the pets. So one of those things will happen.
Mhm.
So we're just going to swap things,
Mhm.
and that is like mutation. But we're going to swap them because we still want to have, we don't want to have duplicate nationalities, etc. So usually mutation is like
Mhm.
setting things on or off, like with genes.
Mhm.
But we're not going to do that here. We're just going to swap things. So
Nice. Okay, cool. So at the end of this, we've then run the simulation, we've evolved the population, and so we've taken pairs of parents and created another 100,000 children that are slightly biased towards the better performing parents, if you like, from the previous generation, and we've got a new generation, which is this population that has emerged. And then we just do the same thing again, Erik. We just check, are any of these now fit? Are they the perfect person? If they are, we return it. That's the solution done. Otherwise, we go again. Simple as that. And I asked you just before we started how many generations we normally need for this, and you said it's quite small. You just ran its test, and it was 10 generations. What have you found a sort of average of this?
I haven't checked actually. I had occasions where it didn't finish, and that's a problem with genetic algorithms too. That they can, I think it's called the local optimum or local maximum, where it's like it's keep on looping in the same area. It's not breaking out, so we'll never get over the hump. But I think this is just because what you said. We have just 14 different score thingies. It's just all very constrained and. Yeah, I had it in 10. I had it in 100, and sometimes I didn't get a result at all. So this is very.
There's a thin line between. Yeah, there's a thin line between having too many things that you're like too much randomness, where you're not really getting towards a conclusion. You're just testing all the permutations. And we've got 100,000 in the population, 1,000 generations. I think you said there's 2 billion possible permutations.
Yeah, we're going to get to that in a minute.
Yeah, we'll get to that in a minute. But at this point, we are sort of hitting, I guess, 10 million possible permutations if there was just randomness in here. So we are sort of walking towards those very large numbers. So you do want to make sure you've actually got this sort of coalescing towards the better performing people. But there is a risk that if you have not enough mutation, as you say, that you just never actually you get into local maximus. But this is very cool. I think this isn't a solution, as you say, that most people are doing. But when I was looking through these, I thought if I was watching this video, this and the Prolog ones would actually be the ones that would be the most interesting that I'd really want to see, because they're not things that you see every day in the world of coding, are they? So
no.
Okay, cool. Anything else you want to say about this, Erik, before we move on to a more normal solution?
No, I try to be even more ambitious, because usually these genetic algorithms, they have like a binary encoding, because that sort of mimics like genes where you have things set on and off. And I was like, oh, there are 5 houses, 5 different variables. So I could fit that in a 128-bit integer. And I initially had that, but I sort of got it working, but there were a lot of bit fiddling and binary ORs and I think it would detract from this actual solution. But that would be more, that will be faster. So and more similar to what people do with genetic algorithms is to encode them as like binary strings. So
yeah.
But you don't need to. You can do it like this.
Nice. Okay. Well, if you feel like writing a genetic algorithm, this is a fun one to solve it with. Let's look at a more common, maybe, approach at least to this. This is Python, and yeah, talk us through this one, Erik.
Yeah. So first is defining a couple of variables. So you see, yellow, blue, red, ivory, green is the sort of like a deconstruction of the range. So there's yellow will equal 0, blue will be 1, red 2, etc., etc. So we're basically giving the variables unique IDs, so their numbers. So it doesn't matter that that the fox and the yellow are both are 0. It doesn't matter at all. But we're going to get to why. So drinks water. It looks nice. So we see for house in solution, which is probably something that we can all understand. If the drink element of house is equal to water, so then we're going to return the nation, and then we found it. So and we do for the zebra one, we do something similar. So that again, that looks deceptively simple. Of course, the meat of this solution is in solution, and solution is you see a lot of nesting here, and there's a function called permutations, and if you've not heard of permutations, permutations of something are all the possible ways in which you can reorder them so that they are unique. So if you have ABC, you can have ABC, you can have ACB, you can have BAC, BCA, etc., etc. So those are the permutations. But the trick is that they become large very soon. So, but we'll get back to that. So we're going to say on line 24, give me a permutation of the nations and assign that to the nations variable. That's probably why the other one has an underscore under it, underscore nation. Then I also want a permutation of colors. I want a permutation of pets, drinks, and smokes. So a lot of permutations. And then we're going to check if that ordering of smokes, drinks, pets, colors, and nations that we have, is that correct? So that is just creating it. So combining them. And then we're going to check if these rules are all applied to this permutation of those values. So that's what's being done here. So check funcs. We're going to go look at that in a second. So those are just the rules. So we're basically saying if all the rules are true for this permutation, then we found the right solution. And there's only one for the zebra puzzle. So so in theory, this is perfect. You just have to encode the functions, and we can probably skip over that mostly. So you see on line 45 to 47 that you get passed in the houses, and we return if there's any house where a nation is Englishman and color is red, then we're good. So these are just the rules. It's just the Pythonic way to write them with like this nice generator expression. And then we have funcs. It's just a combination, a listing of all these rules. So a lot of rules, and then just combining them all. So this was like, oh, this is great. But I knew, because I had been doing this exercise quite a bit, that there is something that must be wrong with this solution. I was like, this must be taking a very long time to run. And I ran it locally, and it was done immediately. I was like, I'm stunned. Is there some magic trick?
Yeah.
And
what? Just explain why before we carry on. Explain why you would expect this to take a long time.
Yeah. So it's because permutations. I explained that were the combinations. So the number of permutations for 5 elements. So we have combinations of 5, list of 5 elements is 5 faculties. So that's 5 times 4 times 3 times 2 times 1. So that's 120. So that's a small-ish number. But if you do 120 times 120 times 120, so you do this 5 times, then you get to almost 25 billion possibilities. And I was like, well, Python is a great language, but I don't think it can run over 25 billion permutations and give me the result within a second. So I knew there must be something wrong with it. And then at first I was stumped, and at some point I thought, oh, this must be happening. So if you go all the way up, if you look at that specific ordering of those variables is actually the solution to the zebra puzzle. So the right ordering of the colors are that yellow is the first house, blue the second, etc., etc. So, and permutations will return all the permutation, but it will give the thing it starts with probably as the first element. So the very first permutation combination that it will check for all of them will be the valid one. So it will just be one single iteration that it will find the solution. So it's basically encoding the solution.
If for these you just did a like sort by random, so rather than this being assigned 0, 1, 2, 3, 4, it was assigned 4, 3, 2, 0, 1. This could take a very long time to run through.
Indeed.
So someone has basically entirely cheated by encoding the solution on the left-hand side, but cheated in such a way that their code is still valid and it still works, but it only works in this very specific situation. And I wonder, when the person wrote this, if they did it properly, left it running for an hour or however long it takes on their machine, and then once they got the results in, reordered them to put the correct result at the front, or if they just looked it up. But if you've solved this, do go and check and make sure you haven't just done a similar thing where you've put in the correct solution, sort of encoded into the way that you're writing the code that makes it run very quickly. But this is sort of the most brute force basic way of solving this, I guess. There's nothing intuitively wrong with it. I mean, it works. But this is sort of approach you would see most commonly if you were looking through different variants.
Yeah, what you probably start out with and then quickly find out, oh, this is not the way that I should be solving this.
Yeah,
at least
slow approach. Yeah. Okay, so if we're talking about tweaking it, we're looking at C now. So talk us through this, Erik. Give us the key highlights of this one.
Yeah, this person had the same idea that I had, where you could use a binary encoding for the houses. And binary encodings can be very efficient. So we have houses with 25 different values that we need to somehow account for. And so we can store that in a 32-bit integer. And we can then apply binary operations on them to work with them, to check whether or not a certain value is set or not. And then first off, that's what's being done here with all these defines. We're basically giving every single one of these variables a specific bit position. So, for example, if you do what you're highlighting, Fox is one shift left to 16 times to the left, and that bit that will be the one for Fox. So either it's a 0 or it's a 1. And of course, later on, we're going to make sure that between bits 15 up until 19, only one of them has actually a single bit set. So we don't want to have 5 bits. They can either be dog, fox, snail, horse, or zebra. So there can only be one. Sorry about that.
Yeah.
But that's the key thing here. So it's just encoding the single house as a 32-bit integer, which makes things very efficient. So
yeah.
And we do that by basically giving them all a specific position. And then there's a bit of bit magic. So owner mask. There's a lot of bit shifting to find just the right values. So you have logic to do bitwise ANDs with a mask. I probably shouldn't be going into this, so I'm just going to skip over it. But what we're going to do with a little bit of bitwise magic that we can go into is later on. So we're going to maybe skip a little bit with these house rules. We'll get back to
these are the main rules that we're encoding again, Erik, with the has's, the implies, etc.
Yeah, so these are all the rules that apply to a single house. So as I mentioned in the Prolog solution, we have 3 types of rules. Most of the rules you can just check if a house is valid. So whether or not if it has an Englishman and it has the red color. So that's you just need a single house. But some of them were next to each other, so you have multiple houses. And there's a very good reason why this has been split in a separate function here. So basically what that hash thing you do is you pass in the house, you pass in that bit position. So we're naming it English, but that's basically a bit position. And then the hash defined under the hood will find that specific bit value and see if it's 1 or 0. And then, probably 1. And then checks to see if it's equal to that other value. So English should be read as the value at this bit position. Okay. So, and this is sort of a bit similar to my solution to the genetic algorithm, where we're going to generate the permutation. It also looks like the Python one. So here, what we're doing here is we have a lot of loops. There's no nesting because they're just listed underneath each other, but in principle, there's nesting. So we're saying we look, for example, for color. We're starting at 10, and we're stopping when it's, not 15. So we're stopping when it's 14. So color will be 10, 11, 12, 13, and 14. So those will be the bit positions for the colors. And within that loop, there will just be, of course, there will be one color. So initially, the first house there, the color will be 10. So I don't know what the first color was when we defined it at the top. And we're saying 1 shifted to the left. So, it's red. And then we're going to do 1 shifted left 10 positions. So then that means the 10th bit, or is that the 11th bit? Probably 11th bit is, this is the 11th bit because we start at 0. That's set to 1. Yeah. So that's what that does. And then you have all these ORs. So we're basically putting a 1 at the position of the number, the owner, the color, the pet, the drink, and the smokes. So we're processing things in 5s. So rightmost 5 bits are reserved for the number, then the owner, color, pet, drink, smoke. So we end up with a house, which is an integer, and it will have 6 bits set. So they also encode the number in the index in the bit. So that's also possible. And then immediately, and this is the key difference with the Python solution, they check if the house is valid. So those house rules, where you can just check all the rules for just a specific house without having to look at other houses, those are checked immediately for the generated value. And only when all those rules are applied and they're valid, will we add it to the list of possible houses. So this is where the Python solution, that should be added there, because this is pruning the total number of results. So you no longer have 25 billion solutions. You have a lot less, because you can already, even though you are doing those 25 billion loop thingies, but it's actually not that bad, because we're not actually generating all the houses, and doing bitwise logic still makes it fast.
So just to compare that to the Python one then. So we are here. So this whole block, is this?
Well, permutations is actually giving us a permutation of a list. And that other one is just giving us integers. So we don't have lists that are being reshuffled, which is way more expensive than just iterating over integers. But it's not doing the cleverest thing that could be, although you probably can't do that in C. But there is a better way to do this. But this is what's possible in C. So permutation here is slightly different, because it's it's a list.
So we're still creating this large list of these things.
Yeah.
Although I don't know if these are I'm guessing
these are numbers too. Yeah.
Enumerators.
Yeah, they're probably efficient. So maybe we just say it's the same thing for now.
Yeah.
But there is no difference between
more efficient because
So we're first pruning things. There is no lazy evaluation that Python has. So we have to get all the houses. So it's sort of like the same thing, but it's doing this bitwise, and that bitwise thing makes it quite fast.
Yeah.
And then there are other rules too. So you have two house
makes it a lot more
rules,
memory
three rules, and but in general, it's the same algorithm, but now applied in a binary way. So you can see here, like for example, complete on line 138. So you have the houses, and you OR them all together, and then everything is like this is the all the bits are set on in the right place. So there's a lot of bitwise manipulation here going on. So, so for the houses here, for example,
I recommend if you're interested in this, you go and read the code rather than us spending more time digging into this.
But it's still sort of like a similar thing to the Python, even though I just said it is, but it is. But the key difference is that this is more, well, it's C, so it's obviously more efficient, but also the binary encoding makes this a more efficient encoding.
Yeah.
But it's not the best that you can do.
No, let's move on to Scala. So I found this one really interesting. So Scala, a similar thing that we've seen, we define some stuff, but then the crucial difference here, and you can see it's quite a short solution, only 116 lines, which is short compared to the ones we're seeing, is how nicely all of the rules are laid out here in a way that is very efficient as well. Erik, you explained to me earlier. This took a little bit of effort for me to get my head around. So, do you want to explain what this is doing?
Yeah, so I'll try. So, what solver returns is an iterator over solutions. So, iterator is you have that concept in a lot of languages. It's like lazy. So it produces a value and then it stops until you ask it for the next value. As a matter of fact, it's actually called next. So if you check on line 17, we're doing solver.next. So that's finding the first value in the iterator. And as there should only ever be one value returned by the solver, that's our solution. But the key thing is iterator is lazily producing values. And so that's very important. But there is a bit of syntactic sugar here that's being applied. So we had permutations in the previous solution from the Python one. We have them here too. So so it sort of looks the same-ish. It's a bit different syntax with the left arrow, but it says nation.permute. So what that does is nation.permute is also a lazy thingy where it gives me all the permutations of the nations. So we get I think it's a list. I don't even know how it's encoded, but we get a list of nations. So, but they're permutations, like with the C# ones where there's, and then we get back one of the values. So and we assign it to nations. So line 22 should be read as for one of the values in the permutation, and then we're going to do stuff with them. But the key part is that we immediately start excluding invalid solutions. So we're going to check if that rule number 10, where the Norwegian lives in the first house, which is something that we can check just by having the nation, we're going to check if that's true. So this is already lazily applying filtering. So
just to look at that in the context of Python, effectively what we're doing is we're inserting in between lines 24 and 25.
Exactly.
We're inserting the rule here. And so rather than just getting all the way down to here with all of this, we're pruning, a huge amount. We're saying we're getting rid of all of the possibilities where the Norwegians in the second, third, fourth, and fifth houses, which is, 80% of our possibilities. We're getting rid of those straight away on this line in between here by checking this.
Which means that
makes it hugely more efficient.
Yeah, absolutely. Because we had 5 faculty, because there were 5 options, and it was 120. But now if we fix one of them, we only have 4 faculty, and that's 24. So that's a huge improvement. So that means instead of doing for 120 nations, we're going to do all the rest of what's underneath it. We're just going to do it for 24. And when we apply this to the other ones too, that will be a massive win. So the next step is colors. So we ask for one of the permutations of the colors, and we're immediately going to do filtering. And we're going to do filtering based on nation and color. And the way that these are ordered, starting with nation and then colors, is, it's the most efficient way, because there are color rules that depend on nation, but the nation rule just depends on the single nation. So smoke rules later on are dependent on colors and nation. So you have to have both of them already if you want to do that pruning. So if you want to exclude all those values. So next to each other on line 31 is a little trick that people have been using, is this getting the indexes, doing the minus, and doing the absolute value must be equal to 1. So it doesn't matter if it's -1 or +1, basically. So that's a little trick that people have been using. But
nice.
So the key part is just that we're already, and now we're having 3 things already that we can prune out. So there's a lot of solutions that are never checked, because we have already verified upfront that we shouldn't even be continuing this path, because we know that it can't ever be the right solution. And that's the key thing. So we're not going to check 25 billion solutions. We're going to check, I think, just a couple of thousand ones, maybe even less.
Yeah.
It's,
and so by the time we're getting down here to drinks, we're running this drinks on a much smaller set by that point.
Massively smaller.
So these checks are only happening, much fewer than you would get in the Python version. And then when we get to the end here, we're just pulling out the data that we want, basically.
Yeah, and of course this is nice syntactic sugar, and under the hood it will be doing slightly more advanced things. But the key part is that this is lazily doing stuff. It's not like defining all the permutations up front and then combining them and then in the end checking them. No, it's giving you one nation, checks if it matches all those rules, and if it does, only then it does it continue. So that's the key thing here, and that's why it's returning an iterator, because it's lazy.
Very cool. Okay, we're now going to look at Elixir, and as we were looking at, we've got 2 more Elixir and Java. As we were looking at this one, we actually realized that it's the same user that's done both the Elixir one and the Java one, but they're very different solutions, Erik. They're 2 totally different algorithms. So kudos to this user for doing that. Also, high rep user, thank you for all of your contributions to Exercism, if you're watching this back. We're starting off here with the rules listed out. This is nice. We've not seen this too much. It's a nice little table to have everything listed like this. I appreciate that. Talk us through what we're seeing here, Erik.
Yeah, so line 2 is defining a house as a struct with color smoke. Okay, we get that. And then drinks water isn't that special. So we do solve, we find the element where the drink is water, and then we get its nationality. So nothing special there. Solve is where it actually, of course, gets interesting. So we start with something called a seed. I'm slightly uncertain why the seed was hard-coded, because I guess it should maybe be random, but it's fine. This isn't at least the seed that is already the right solution. So
yes, it's a wrong seed.
Yeah, it's a wrong seed. It's very deterministic because you have a fixed seed. So maybe that was the key thing but this is just a combination of houses that's not entirely correct yet. And we have to find the correct one, but we have to go down a little bit for that. Okay, so if you ever heard of depth-first search, which is a way of searching a search space, and ZebraPuzzle, of course, has a search space. We've just been mentioning that with the Scala one, where we just want to search as little of the search space as possible. This is depth-first search is one of the ways in which you can do that. And we're going to start on line 75, which has a call to do solve. And then it starts out with creating a list with a single value, which is the seed, and a map set. And the first first argument to do solve is the list of things that we have to check. So these are candidate solutions, things that could be the right solution. And then the second argument is a set of things that we've already checked and that we know aren't right. So On line 78 is just a check that if we ever get to a point where we don't have any candidates, then it must be an error, because there is a solution to the zebra puzzle. We know that, so then we would have made a programming mistake. But if there is at least one element in the list of candidates, so we do a little bit of deconstruction. So we have cum, that's like the candidate, and we have remaining. The upfront check is to see if have we already seen this candidate. If so, we're going to skip it and we're going to continue with the other candidates. So that's just a way of preventing having to recheck a solution that we've already seen. Then we have a lot of rules. So we have references to functions. And these functions are then piped into an enum.reduce, which is a higher order function. And you initially pass in a tuple of an atom OK with remaining. And remaining are the rest of the elements. So that's the tail, basically, of our candidates. And the way that you should remember that these rules will be working is that they can add things to the list of things that we need to check. So to the list of candidates. So we're going to check all these rules. And if we find that a rule is invalid, we're going to try and add possible valid solutions to our list of things to check. So that is the general gist of this implementation. And we're going to see how that works.
So
here you go.
Just to start us off then, so just to talk that through. So we've got this seed. So this is a list of these 5 different houses. So one set of things effectively. And then we're passing in that as a list. So in this first call we're coming to, we've got the combination, which is going to be seed, and then remaining is going to be an empty list. And obviously seen is also an empty list or an empty map set. So we can guess without looking at this that it's not going to be. So we can ignore this for now. Instead, we're coming here, we're creating a list of all of the rules, piping those into reduce with OK and what is currently an empty set.
List,
I presume that stays. Empty list.
It won't stay. No.
Yeah, it won't stay as an empty list. So do we need to look at what these are doing?
Well, maybe we can look at what we're doing at the end, because that's simpler. So then what gets returned with that enum.reduce is one of 2 things. Either it's OK and then something that we don't care about. So we don't care about any other candidates because we found the right solution. That's basically what OK says. We found the right thing, and we're going to return that combination. Otherwise, we're going to say we have to continue searching because we haven't found the right solution. And we're going to, the queue is like, what's the new queue? So having processed all these rules, this is the new queue with all possible new things that we think that we should check. And then we're going to recurse and we're going to process that queue. But we're going to mark this current combination as we've already checked this and it's not valid. So the trick is now to look at those rules and how do they work.
Yeah. Which one do you want to start with, Erik?
Well, maybe just do that one. So rule number 2 is Englishman lives in red house. So it calls into a helper function called house rule. We pass it in the combination, so the houses. We pass it in, I don't know, a keyword argument or whatever that's called. I'm not sure.
The details of the rule.
Whatever. It's a list of combinations of keys and pairs. And then we pass in that accumulated value, which was initially OK remaining. So we have to remember that. So that's the... so maybe then we go to house rule and see how that is defined. So that's all the way down to the bottom. Where is it? House rule. Yeah. So house rule, we're checking whether there is a house for which there are 2 attributes that have those values. So we're trying to find the house with those values. So first value, second, and then there's a call to another function. So It's quite well factored. So swap attributes is actually below this. So the first thing that we see is swap attributes with a guard clause on line 225. So we now have the combination. We have an index of the house with the first attribute and the second and the value. No, 225.
This one?
225. When not is nil.
That's 225.
Oh, 215. I say 225. Yeah. Pardon me.
Okay, sorry. Yeah.
English. So that's basically checking, hey, did we actually find those two houses? And are they the same house? So in house, we try to find the house where the house had the attribute with the right value. And we try to find, well, another house or maybe the same house with the second attribute and the second value. If they are the same, we both found them, that those not is nil checks, then this is the right rule. So we found a solution. We don't have to do anything. We're going to continue with the other rules, basically. However, if that is not the case...
So at that point... Sorry, what's this do accumulator doing?
Yeah, we're just returning. We're not adding anything to the queue of things to check, basically. So we're saying, hey, we're still in the same state that we were before. We don't have to add anything to our queue.
So this accumulator was...
That was that okay remaining thing at the beginning.
Things that have around.
Yeah.
This is the remaining, is it?
Yeah, yeah. Well, it's that entire thing. It's okay.
So we're not adding any... Yeah.
But, yeah.
Okay.
Okay, so, but of course, it's more interesting if it isn't. So on line 218. So this time I am correct. So what we're going to do, we know that it wasn't valid. So they were, we couldn't find those values. So what we could do is we could swap things around. So if this wasn't the right ordering, maybe if we swap things around, then it is right. So we can either swap the attribute in the two houses, the first attribute, or we could swap the second attribute in the house. It could both be valid things. Could both are the things that make it valid. So what we're going to do is we're going to, on line 200, we're going to do a swap. We don't have to get into how that actually works, but just swapping the attribute from one house to another house, and that basically they have their value swapped. So we get two new candidates, and on line 222, we're saying, hey, prepend those values to the list. So this is why it's a depth first search, because we're gonna put it before at the beginning of the queue. So these will be checked first in the end. And we're saying we're changing the first thing from not okay to cont. So this means we haven't yet found the right solution. It can't be the right solution because a rule didn't match. So it can never be okay. So we always have to start checking new candidates. And we add those two swapped candidates. So in the end, it will do this for all the rules. So there might be more house rules that add more candidates. But they will all be added to that list of candidates. And in the next check, it will do the same thing. And hopefully it will find that these are right. But this is not just random search, because we have information. And we're sort of doing a very guided search in the search space, where we know that maybe swapping things around improves things a bit, etc. So it's not just our randomness of this C# simulation. This is directed search.
Yeah, it's somewhere between the genetic algorithm and the sort of fixed permutations, isn't it? It's like a more of an in-between version of that. So yeah, again, there's a good 230 lines of code here. I mean, a lot of this is the rules as you would expect them, but I do recommend, again, going and looking through this code, taking your time. It's good functional coding practice, make sense of all of these different lines and how they all sit together and play together. The first time I saw some of this, I was a bit like, okay, it's going to take me a minute to get my head around. I'm pretty sure, Erik, you would be the same, even though you're probably a lot more familiar with some of it. Yeah, do go and take a look through it. But I think the way you explained that there, Erik, it made sense.
No, I actually think this is quite a really neat solution. I actually didn't see anybody do something like this, but maybe I just didn't find it.
Yeah, it's really nice.
I liked it.
So, same author, now in Java, and a totally different algorithm. This is the AC3 algorithm. He's left a nice comment at the top to tell us. Do you know what the AC3 algorithm is, Erik? Can you explain that in a sentence or two?
I can, because that you actually posted a video of a professor explaining the algorithm, which I watched. So
Nice.
the AC3 algorithm is a constraint solver algorithm. So we've thought about constraints. So what you have is you have variables, and variables have, well, they call it domains. And domains is are a set of allowed values for that variable. So suppose, well, in this case, we have colors. And so, for example, the color red, we can have them at the domain 1, 2, 3, 4, 5, which means that they would correspond to the house index. So the color could be at house 1, 2, 3, 4, or 5. So red, but blue could also be in 1, 2, 3, 4, or 5. So initially, all of our values or our variables will have the same domain. So the domain will be 1, 2, 3, 4, 5. So that's our initial state. However, we have rules, of course. So we know that, for example, there is a rule where I think green is the rightmost house. We have a rule where it says that for this specific variable, there is a limitation on that domain. So, you would have this whole list of rules, and you would go through these lists and you would check, hey, for this variable, does its domain make sense when you look at it from this rule standpoint? So if you would find that you would, for example, for the variable green, if it's if the rightmost if it has as a domain 1, 2, 3, 4, 5, but we know that it can only be 5, we can scratch away all these other values. So that is great. So we've limited the domain of the green variable, but we know that these other variables, they all have different domain values. So we know that as green has only one value, the others can't have that value. So what we can then do is the algorithm will see that, hey, we've changed green. These other variables are dependent on green. So we're going to update them again. And we're going to basically recheck if the domain is still the same. And in this case, we know that, hey, no, we have to cross off that rightmost value because it was already taken by something else. So we're going to limit the domains. And then if they are changing, maybe their dependencies will change too. It could also be green again, but in this case, it doesn't make sense. But you get this whole list of rules and you keep on crossing off domain things until you've reached the end. And that is the
nice.
Sorry, you go.
I was going to say a nice parallel to what you were just saying as you were saying that. I was thinking it's exactly how you solve a Sudoku puzzle, which is another constraint-based algorithm. But it's it's exactly what you're doing. You're putting the number 3 in there, and then you realize, well, okay, that means there's got to be a 3 over here. Well, there can't be a 3 there, and it's that sort of the step-by-step breaking down of things. Which is exactly what you use that for mentally, naturally when you're doing stuff. But effectively, if you apply that Sudoku mindset to zebra puzzle, you're getting the sort of algorithm I think you're talking about here.
Yeah, exactly. It's perfectly. It's a perfect analogy.
Yeah. So looking at this solution, then it's long. I mean, we've got 500 lines of code, more than that. Nearly 580 lines of code. So we're not going to talk you through all 580. But I guess there are two sides to this, Erik, that's sort of useful to see in brief. One is the actual AC3 bits of this. And then obviously there's a whole extra section which are the sort of rules that you're looking at for this particular puzzle. Because actually a lot of the AC3 stuff is just quite generic, isn't it? It could be totally for anything.
Yeah.
You could probably keep 70% of this code if you were going to solve Sudoku with it. So where's the best place for us to start?
Probably a little bit
maybe
up.
in this.
So where you now? That's a just move a little bit up.
Yeah.
So, yeah.
I think here.
So this is this reduce method. It takes in you see a map. And that's what I mentioned. So for each variable, there is a domain. And the domain is, in this case, a collection of integers. It could have been a set in this case. But it has a set of possible values. So it's well named, the domain by variable. So that's quite interesting. And then args is the terminology of the AC3 algorithm. These are the rules. So you have an arg between one variable and another variable when there is like a dependency on it. And there are interesting parts about the algorithm where it works both ways, because you only update the leftmost part, but let's forget about that. So so here on that line, we're gonna see which of, if you have a variable, which of the args are, interested, it says, so which have a relationship with that variable, basically. So we're gonna check if, we're gonna keep a list of, these are all the things that need to be updated when this variable's domain changes. So that's how you should be reading that. So whenever something changes for this variable, update, we have to also check these other rules. So this is an example what I mentioned with the green color changing, means that you also have to update the domains of the other colors. And then there's a queue, which is actually something like similar to the Elixir one, where you have a queue of things to check. So initially it has all those args that we just mentioned, and it will keep on looping while there is stuff to do. So on line 539, we get the first element in the queue, and then we do arg.check with the domain by variable. So this is checking a rule, and it will return true if something has changed. So if we, for example, we crossed off a value, or we crossed off multiple values, whatever, then we know, line 541 is just a check if the domain is empty, which shouldn't happen for this case. It's just generic code. But just suppose we've changed something, then we're gonna find out all the other elements that need to change, and we're gonna add them to the queue. So all the rules that we need to recheck, basically. So not specifically elements, rules, args in this case. So and this is like a repeating repeating algorithm. So we're checking variables, see if they still match, depending, all the rules are still applying, and if something has to change, then we need to see if that might influence any of the others. But because we have defined the rules between variables, we will know that if we change variable A, that we also have to check B and C, because they are in rules with A. So that is a key part of the bookkeeping.
So looking at then a couple of these things, so if we look at next to, for example, so we're saying one house is next to the other house. So we have this arc that is this relationship between these two values. And then we have the sort of function that gets called. So exactly like you're saying, if one of these changes, then we need to trigger this other thing in response, basically.
Yeah. So maybe if you go up once, there's also another next to, and I think it doesn't have an offset. Yeah. So so this is checking. So you have a left variable and a right variable, and on where you were now highlighting, that's like the anonymous function method that's being called. So we're going to say left domain dot remove if. So we're going to remove a value of left domain's values if the right domain does not contain value -1 or and not contains value +1. So basically all the values that are not next to the value of the right domain, they must be removed, because, if you're next to each other, they have to be like within the range of 1. So this is crossing off invalid domain values.
And the same house, obviously, is an obvious one. You're specifying these are the same things.
That the elements within the houses overlap, basically. Yeah. So we're removing anything that isn't in both.
We also have the concept here of mutually exclusive things. So these things have to be different.
And this is also well commented in code, by the way.
So, yeah, it's really nice. It is, like, you can read it through and make sense of it, which at 500 lines of code would feel overwhelming if you didn't, for sure. Is there anything else that's worth talking about?
No, maybe just show the list of args so that you can see that that works both ways, so that you can see how this is actually combined. I think it's a bit up. We're quite a bit up. or maybe search for arcs. I think that's the method name. Yeah, that one. So
There's a lot
just
of
a little bit below.
lot of art.
Oh, you were there. I saw the list of.
Where here?
Yeah, there. Yeah. So those are the rules. So you see that the same house arc depends on as the left variable Englishman and as the right variable red, but also the inverse. And once again, that is because the algorithm only updates the domain of the left variables. So for the other one to also update, you need to recheck it. And that's what was done in that algorithm, where we can see that, hey, if the left variable changes, then we know that we have another arc where it's the right variable. So then we need to specify that arc too. So yeah, and so
very cool.
Yeah, it's a very cool implementation. It's a cool algorithm.
Yeah,
and indeed, if they would have like extracted all the arc stuff, then it would be a lot less code.
So yeah, congratulations to Cargo. I'm hoping I'm not totally destroying your name. I'm sorry if I am, but for these two really good solutions, and again, thank you for all of that rep that you've earned. No doubt contributing and mentoring on Exercism as well. That brings us to the end of the video, Erik. That was really fun. It was we spent probably half an hour before the video started just talking through these as well. And I really enjoyed just seeing these different ideas and different approaches. I think I found this exercise more than others to be quite like inspiring from a enjoying code perspective. I know a lot of the other algorithms and other things we look at are maybe things that are a bit more practical or a bit more like comparing languages, but it was quite nice to just compare totally conceptual approaches. Like you could write your generic algorithm in any language. It's not really about the language, it's about the conceptual way of solving things. So yeah, it was really, really fun to look at that. So thank you for talking us through those. Thank you for a great Prolog and C# solution yourself, Erik. They're really cool ones to see. I hope you enjoyed watching this, everyone. Please leave a comment. Tell us which of the solutions you liked, link to your own solutions. You can make lots of suggestions about how its genetic algorithm could be better. Sorry if I've been saying that wrong for the whole of the video. And yeah, please do give this a thumbs up and share it with people if you enjoy it. And don't forget to subscribe for more videos as well. And see you soon. Bye for now.